a little bit more formally. So what's going to happen here is we're going to still be talking about that conditional probability, but now how it applies to independence. So determining if events are independent from one another or not. So yesterday, we did some stuff like we did with the sequence of events, drawing a king, then a queen. So we're going to go back to that discussion here and talk about how it pertains to this idea of independence. So first thing, when we say events are independent, we're saying that the first event does not affect the outcome of the second. So thinking of it in terms of a sequence of events, if the two events are independent, it means that no matter what happened on the first trial, the probability for my second event remains unaffected. Whereas dependent events then do affect one another. And so yesterday we talked about drawing cards with and without replacement. So in this first scenario here, I want to find the probability, or if we're saying we're going to select a king, then a queen with replacement. We want to know, are these two events independent? So in this particular scenario, if I think about selecting a queen just in general, since that's my second event here, when I select a queen in general, I have a 4 out of 52 chance of that happening. But now if I throw that condition on here that we've chosen a king already, in this particular scenario, because we have the with replacement, that was the thing we kind of focused on yesterday, was that key word. So the fact that we have with replacement here, that means when I selected my first card and it was a king, I put it back into the deck, shuffled up, and redrew. And so when I think about the probability of drawing a queen after I've drawn a king, it doesn't change. I still have a 4 out of 52 chance because I replaced the king before I redrew. But then we talked about doing the same thing, but without replacement. And so again, if I'm thinking about this idea of drawing king, drawing queen from a standard deck, on its own, again, the probability of drawing a queen is 4 out of 52. This time, if I draw my first card and don't replace, so now I select my king and I keep it. Now when I go to find the probability of selecting a queen, my probability has changed. I have the 4 queens that I could still select from, but I only have 51 cards left to choose from. So in that first scenario, drawing a king and drawing a queen were independent of one another. It didn't matter if I drew the king first or not. The second draw, I was going to have the same probability of drawing a queen as I normally would. But without replacement, the minute I remove that card from the deck, I've changed the probability of getting my queen, and so now I have events that are dependent. And so that's the basic idea for today's lesson, this last little bit of the unit here. If we want to determine if events are independent from one another, then the probability of my event on its own needs to be the same as the probability of my event given that the other ones happened. So when they describe a scenario to you in the homework, they're going to ask you, are the events A and B independent of one another? And so you're going to check to see if this equality holds. Now keep in mind, if I'm looking at A and B and testing for independence, I could also find the probability of B on its own and then calculate the probability of B given A to test for independence as well. So it doesn't matter which event I choose to use, but I'm going to pick one of the two events and I'm going to calculate its probability on its own. If I were just to randomly select one individual, select one card, whatever the case may be, what's the probability of getting that event? Then I want to look at it as what's the probability of getting that event if the other events happened. If my probability remains unaffected, if these two probabilities are equal, then it means that second event had no effect on the first. And they're independent of one another. If these probabilities are different, then the one did affect the other, and so they're dependent. Now the other thing to be aware of, another test you can use for independence, is we can use two conditional probabilities. So I could do the probability of A given B and calculate the probability of A given not B. So whether B happens or B doesn't happen, if the probability of A stays the same under each condition, then it means A is unaffected by B, whether it happens or not, and the events are independent from one another. So these are the different relationships we can use, but you have to pick one of these relationships and test it. Now when I do these, and as you'll notice on the answer key, so I think I have a couple where I have both options shown, but for the most part, I typically stick with this first relationship here, the probability of A and the probability of A given B, simply because calculating a straight probability is usually a little bit easier than the conditional probabilities if I'm trying to calculate two different conditional probabilities. So when you're looking at these types of problems, think about your two events. Think about what the conditional probabilities would look like. Sometimes they're both easy enough to calculate and it doesn't matter. Sometimes one conditional probability is a lot harder to calculate than the other. So then I want to adjust what I'm testing for accordingly. But as far as independent events go, we've got to test one of these relationships and show that they're either equal and therefore independent, or they're different and they're dependent. So an example here, so is there a relationship between the subject being taught, so a teacher teaching a certain subject, and their handedness? To find out, researchers chose an SRS of 100 teachers at an education conference. The two-way table summarizes the relationship between the subject being taught and the dominant hand of each teacher. So suppose we choose one of the teachers at random. Are the events that they teach math and that they're left-handed independent? So if we think about what we just discussed here, I've got the events teaches math and left-handed. I want to test to see if those are independent. So I'm going to pick one event or the other. It shouldn't matter either way. So if I choose teaches math as my event, the first thing I'm going to do is I'm going to calculate the probability that if I select a teacher at random, that teacher teaches math. So just on its own, what's the probability that when I select from this group of 100 teachers, they're going to teach math? So 46 out of 100. So there's about a 46% chance that if I select a teacher at random, they teach math. Now, once I've calculated that probability, Now I need to look at this in terms of that left-handedness as well. So now we're going to say, okay, if I know they're left-handed, so that's the key here. I want to say I know they're left-handed. Does that affect the probability that they now teach math? Because if knowing that they're left-handed doesn't change my probability of selecting a math teacher, then these two events are independent. One doesn't affect the other. But if my probability changes, then the one did affect the other, and I have dependent events. So then the second thing I'm going to do is calculate my conditional probability. I'm still testing for teaches math. That's still my event. But now I'm throwing the condition on there that the person is left-handed. So now I'm telling you, you're selecting a left-handed teacher. We want to know what the probability is that they teach math. So based on our discussion from yesterday, if I calculate that conditional probability using this two-way table, what's that going to look like? Seven out of 10. So my probability that they're left, or the number of left-handed teachers was 10. 7 of them taught math. So if I know they're left-handed, I have about a 70% chance of selecting a math teacher. So when I look at the two probabilities, did they remain the same? No. Knowing that they were left-handed increased the probability that they were going to be a math teacher. So knowing the first condition affected the probability of the second. So these would be dependent events. Okay? Now, just to show you, okay, thinking about the other options that I have here. So I chose to take math as my event. I could have just as easily have done left-handed on its own too. So if I wanted to, I could have said the probability that I get a left-handed teacher, which in this case would be 10 out of 100. So about a 10% chance. Okay. And then since that's my event, I'm going to compare that to the probability that they're left-handed given that they teach math. So this time, I know they teach math. So there's 46 of them. 7 of those are also left-handed. And so if I take 7 out of 46, I have a calculator that can throw it in real quick. Just so we can see the decimal. I think it's around 15% or something. Okay. So the probability that they're left-handed, given that they teach math, jumps to 15%. So again, even though they're different percentages that we calculated, the percentages changed once I threw the condition on. So knowing they taught math increased the probability that they were left-handed. So those are dependent events. Okay? So, however they present the information to you, whether it's a two-way table, they just give you percentages in the problem. When you're testing for independence, you are checking those relationships. What is the probability of one event on its own versus the probability of that event given that the other has happened? Okay? And then the last thing here, so we talked about this conditional probability, right? If I have mutually exclusive events, so here's the other thing we want to tie in here. So we started talking about mutually exclusive events last week. If I have mutually exclusive events, and I think about this idea, this relationship between independence and mutually exclusive. We talked about this yesterday. If I have mutually exclusive events, what happens to my conditional probability when I put the two events together? So what did it mean to be mutually exclusive, or what did it mean to be disjoint? They don't have any overlap, right? There's no outcomes that work for both. So we talked specifically about how that pertains to conditional probability yesterday. If I have disjoint events, if there are no outcomes in common, what happens to my conditional probability between those events every time? It goes to 0, which means if I have mutually exclusive events, can they be independent from one another? So think about our relationships back here. If they are mutually exclusive, what's going to happen here every time? It's going to go to 0. Going to go to 0. Going to go to 0, right? So anything I do conditionally goes to 0 with mutually exclusive events. So can mutually exclusive events be independent? They cannot. So that's something you may want to get in your notes there. If your events are mutually exclusive, they cannot be independent. And maybe even more importantly, the converse of that also holds true. If I know the events are independent, then they cannot be mutually exclusive. So if I know that they're independent to begin with, then they cannot be mutually exclusive. Okay? So we want to make sure we're kind of aware of that as well. And then here are the problems that you want.